Okay, let us see the next example whereby we have a recycle without a reaction. So in this example, there are two units of equipment, which is evaporator and crystallizer and filter. It's a combination of crystallizer and filter. And there's no reaction here. However, you have to take care about the phase of the phases of the chemical, okay, the phases, which is it is in a solid, in a solution, and some of it in a liquid, and also in a gas form. Okay, so what we have here, you are lucky here because you already have this block diagram. It came together with your equation. Okay, so you don't have to draw your own block diagram. Okay, the equation already draw it for you. So you have here is a process of recover. There is a process to recover crystalline potassium chromate from aqueous solution. Okay, meaning to say it is an aqueous solution. There are potassium chromate and also a water, right? H2O. Okay, let's read the equation. Okay, so 4,500 kilogram, 400 of a solution that is 1/3 of potassium chromate, 1/3. Okay, 1/3, 1/3. By mesh is join a recycle stream. Okay, join a recycle stream that contain about 36.4% of potassium chromate, and this combined stream will fit into the evaporator. Okay, evaporator is one type of equipment. It's used to evaporate water or any chemical that been evaporate, that can be doing evaporation process inside it. Okay, and the concentrated stream leaving the evaporator contain, okay, another composition that leaving the evaporator, and then this stream is fed into a crystallizer in which it is cool and cause the solution to came out, cause the crystal forming, and it been filtered. Okay, and then the filter cake consists of potassium chromate crystal and a solution, and then 36.4% is the solution itself, and then the crystal account for 95% of total of the filter cake. The solution that passed through a filter, also 36.4, is recycled back to the evaporator. So you need to calculate a rate of evaporation, the rate of production of crystalline, the feed rate that, okay, the rate of evaporation, the rate of production, the feed rate that evaporate to the evaporator, and the recycle, okay, the mass of a recycle over the mass of fresh feed. Okay, just like this, the same like previously as you calculate the recycle ratio. And for B, what happen if you don't do a recycle? What happen to the production rate if you don't do a recycle? Okay, and what are the benefits and costs of the recycling? Okay, we have to compare between the production rate of crystal, which one is higher, and which one will cost, which one is more benefit, which give more profit. Okay, so this is the block diagram. Okay, I just enlarge it and put another additional information. For example, the equation state that it is 1/3 of potassium chromate. Okay, so here for the potassium chromate, we put it as a K, and for water, we put it as a W. Okay, So because of 1/3 is a K, which is potassium chromate, another 2/3 is a water. That's why it get this value. Okay, and then the question also mentioned about recycle stream having 36.4% of K. Okay, and the rest would be a water, because this is a solution, is a aqueous solution of potassium chromate and water. Okay, and then the question also mentioned about the same composition of water and potassium chromate being filtered out, and also we have a filter cake. Okay, not a cake that you eat. Okay, this is also called a cake, but it is not the same cake that you eat. Okay, it actually in a solid form. Okay, as you can see here, it is in solid, whereby here it is a solution, or it is in a liquid phase. Okay. The first thing you have to do is you have to number the stream. Okay, 1, 2, 3, because this stream we have to number for easiest for us to put the unknown. Okay, so I rewrite this, okay, based on the sentence or based on the previous slide. Okay, previous, this is given by the question, so we have to interpret this information and rewrite it again in the form of this one. Okay, so easier for you to understand it. Okay, so the same method. Okay, next what we need to do is we have to do a boundary. We have to define the unknown. For stream number 1, we don't know the mass, so we put it as an M1. We don't know the composition of K, we put it as X1, and the composition of W, basically 1 minus X1, because it only have 2 components. Same goes with stream number 2. And because of this is an evaporation process, meaning to say the water been evaporate. That's why at this stream we have only water, and it is in the form of vapor or in a gas, because the liquid water, when it evaporate, it turn into a vapor water, into a vapor phase. Okay. And then there is stream number 3. Okay, we don't know the mass M3, but we know the composition because 49.4 is stated in the equation. Later on, you can go back to the equation. Okay, so same as previously. Okay, you might be boring listening to this, but I have to keep on repeating this so that you really get the idea how you're going to do the material balance on a multiple unit. Okay, sorry that I have to repeat this. You can fasten the video if you don't want to listen, but it is still the same, which is you have to set a boundary condition. You start with overall boundary condition, and when you have this boundary condition, you should have a degree of freedom. Okay, you really need to do a degree of freedom because you want to determine at which boundary condition you can solve it first. Okay, without doing a degree of freedom analysis, you might end up a long way. Okay, meaning to say you just keep on just trying, and then you cannot solve some of the unknown directly. So the easiest way for you to do it is to do a degree of freedom, and you start to solve the unknown from 0 degree of freedom first. Okay, so this is an overall degree of freedom. It's 0, meaning to say you can solve directly for the value of M2, M4, and M5. Okay, and another degree of freedom at the evaporator itself, you have 4 unknown. Okay, and please fill in your lecture note, okay, and then you have only one unknown, which is can be determined from this to this. Okay, you left another 1 degree of freedom. How about at a mixing point? Okay, same, you have 1 degree of freedom. Okay, you have 3 unknown, but you only can do 2 balance of a species, so you will left another 1 degree of freedom. And then at the crystallizer itself, okay, at the crystallizer itself, you actually originally have 4 unknown. Okay, however, 2 of the unknown can be determined from the overall degree of freedom. You can determine directly. Okay, M4 and M5 you can determine, and you have another balance for the water and for the potassium chromate, so you have 0 degree of freedom. Okay, so repeat again the same procedure. Okay, so you start with 0 degree of freedom first, which is at the overall boundary condition. Okay, a balance for the before that, the question also mentioned that a solid constitutes 95%, meaning to say the value of M4, okay, the value of M4 is basically 95% of M4 plus M5, okay, meaning to say in that stream, 90% of that stream is the cake. Okay, so you get this equation. You get this equation. Okay, we put it as equation 1, and then we do a overall balance for the potassium chromate. And remember, this is non-reactive, so we just directly use input equal to output. Okay, so the input basically this one, okay, time with 4500, that is the input, equal to output. The M4 is the output plus the M5. Okay, together with the composition, you have equation 2. We put it another equation because we cannot solve it directly, but we now having 2 simultaneous equation which we can solve together, so we can determine the value of M4 and M5 directly. And remember, the question asking you about the rate of production of crystalline, so which is the value of M4. So you can determine the value of M4 as so you can determine the rate of production of crystalline. Okay, and then you can solve for overall. Again, at the outer boundary condition, you can solve for total mass because you can calculate the value of N2. Okay, for the overall total mass balance, okay, you can determine the value of M2 since you already know what is M4 and M5. Okay, so you can determine the value of M2, which is the rate of evaporation. Okay. Okay, so at a crystallizer, we want to determine the value of M3, okay, because we already know what is M4 and M5, so we want to determine the M3 and M6. Okay, start with input equal to output. We have M3 Okay, this is a mass balance. We have M3 equal to M4 plus M5 plus M6. Okay, so because we already know what is M4 and M5, you can get one equation that relate between M3 and M6. Okay, and then the value of M, you can do a water balance, okay, to find another relationship between M3 and M6. You can do a water balance. Once you do a water balance, okay, you can get another equation, equation number 4. And when you solve equation 3 and equation 4, you can directly get the value of M6 and M3. And M3 is basically a feed rate to the crystallizer, as the question asking you to determine. Okay, so this question is quite tricky because it doesn't asking you directly what is M3, what is M4, what is M5, what is M6, but it's asking you another term. What is the feed rate? What is the production rate? And you yourself have to determine which M represent a feed rate, which M represent a production rate. Okay, and the recycle ratio, basically the M3 over the fresh feed, 4500, our fresh feed. Okay, so what left? Okay. We left only M1 and X1 to be determined. Okay. So you can choose either to do at a bound, you can decide whether to put a boundary condition at a recycle fresh mixing point, or you can do at the evaporator. Okay, let's say if we choose at a recycle fresh mixing point, you have input. Okay, you have input equal to output. Sorry, you have input and another M2, M6 also is an input. Okay, and equal to M1 is the output. So you can determine that directly your M1 since your M6 already determined previously. Okay, and then the feed rate to the evaporator, also the question asking you the value, right? Or you can choose a boundary condition at the evaporator whereby you already know what is your M2 and M3. You can straight away get the value of M1. Okay, so it should be just the same value. This also one of the method if you want to recheck whether your calculation, your M1 is correct or not. Okay. Okay. So you have already determined all for question A. How about for question B? For question B, basically, what happens if you don't recycle? What happens to the production rate if you don't recycle? Okay, when you have an evaporator, crystallizer, okay, and then you don't recycle anything, you just discard. Okay, so without recycle, we don't need that recycle stream. So you can straight away do a mass balance. Okay, just do a mass balance at the evaporator. Okay, and you get directly the value of M1 and M2 as one equation. So another water balance at evaporator, you get another equation. So you solve directly, you get what is the value of M1 and M2. Okay, and then without recycle also you can just directly do a mass balance at a crystallizer and mass balance and also a water balance Okay, you will get another equation, equation 3 and equation 4. Okay, equation 3 and equation 4. So you have to solve. You use another information which is M3 is 90% of the filter cake. Okay, a typo here, filter cake. Okay, and then you get straight away get the value of M3 and M5. Okay, so you can compare without recycle and with recycle. What happened to the value of M2, M3, and M5? You don't need M6 here because you don't recycle.